My mother always told me that once infected, I must just let the infection run its natural course. She assumed that the whole process from infection to disease symptoms through to recovery was predetermined. And some intervention may help release the severity of symptoms, but basically I must just lie there and suck it up. Her logic was she'd experienced the process, so had my older siblings, and now it's just my turn to suffer. To some extent there's some truth in this. If you look, incubation periods, infectious periods and time to recovery are fairly consistent for an infection, but vary between different causative agents than an agent varies between individual hosts. In epidemiological models, we often use many of these parameters and just simply say they're the same, quite similar, and we have set periods. The underlying assumption is that there's a homogeneity across the population of susceptibles, such that any host-to-host variation is really trivial and of little importance to the nature of the larger epidemic. In reality, this may not be the case. There can be a great deal of variation in the number of secondary cases generated by an infectious host. This can be because some individuals have a particularly long infectious period, because they shed a large number of pathogens, or quite simply because they have many contacts. In some cases, all three may act together, so the infected person does not show symptoms, keeps shedding large numbers of pathogens, and has a high contact rate with the other susceptible hosts. That is, an asymptomatic carrier. An example of this is Mary Malone, or what's become known as Typhoid Mary. She was one of the best known examples of an asymptomatic carrier. We do not know whether she suffered a normal infection and then just harboured the Salmonella typhi infection that causes typhoid fever, or she never showed any symptoms at all and was always an asymptomatic carrier. What is apparent is that she became an asymptomatic carrier for at least 38 years and right up to her death at the age of 69. She was a cook. And what was truly unfortunate for her victims was that she did not believe in washing her hands. So as she moved from job to job, preparing food for other people, she infected them. They became ill, and then she would just move on to another job. She infected at least 50 people, 3 of whom later died. There is no doubt that she was an exception to the average infectious case. She infected a large number of secondary cases. She was, in effect, a super spreader. Now, this term super spreader was first coined in relation to the SARS outbreak in 2002 and 2003 to describe the large proportion of secondary cases that arose from a very few number of infected individuals. The first case in Singapore was an airline steward who brought the infection from a hotel in Hong Kong and then infected a large number of individuals, most of whom later died, including her family, her friends and her priest. Another individual, one she infected 143 individuals, including all the doctors and nurses that treated her, while by far and away the majority of infected people never infected anyone at all. So if we were to describe this statistically, what would be the expectation for the frequency distribution of secondary cases per infected host? Our first expectation is that this should be a random distribution. Some individuals will infect none, some in few, but nobody infects a very high number. Indeed, with the SARS situation, this was not the case. In this instance, where we have the data, we can show that there is an unfair distribution. A small number of individuals cause the majority of secondary cases, and there are a large number of individuals that don't infect anyone at all. From the data available on SARS, seems to have the smallest proportion responsible for the most infections. But we also see similar patterns in measles, monkeypox, smallpox, pneumonic plague, and many other diseases. So this might be much more common than we previously thought. Now, there are 2 very important consequences for the discovery of super-spreading events. First, when the highly infectious individuals are also the most susceptible, that is, the more likely to get the infection, then an infection which invades a population will spread faster, it will effectively have a higher R0 and would be more likely to spread than one where the hosts are all the same. Second, at the same time, if we can identify the characteristics that could identify what determines a spreader, then we could just target these few individuals for treatment or intervention of some kind to reduce the likelihood of an infection getting established and spreading through the population as a whole. What a great money-saving approach that would be. If we could identify the target, say just 20% of the population, to stop the disease, we could have a very big impact indeed. Now, one of the infections I've been working on is a disease called tick-borne encephalitis, which kills children in Asia and Eastern Europe. And it's a disease that is passed from wild mice to humans by ticks. We have found that in the mice, it is the larger mice, the middle-aged males, that pass this infections to the ticks and then to the humans. So if we could target them, then we could stop the infection ever getting to the children.